Okay, thank you. Thank you for the introduction and for the invitation. The talk will be divided into 4 parts. So the first part, I'll try to introduce what are Calabi-Yau manifolds by having a recall, like some basic recall on complex geometry, Kähler geometry, and then get into Calabi-Yau manifolds. Then I'll talk about Calabi-Yau manifolds with isolated conical singularities. This is what I refer to as Calabi-Yau conifolds. And we look at the algebraic ways of desingularizing these that are resolutions and smoothings. Then we will introduce the question we're interested in, and we give the language of manifolds with corners that will be of use to the way to attack this problem, and then we'll see an idea of how to prove this the result. So starting by complex manifolds, so the most basic way of defining complex manifolds is these are spaces which have an atlas of charts to Cn, and the transition maps are holomorphic. So the same thing as smooth manifolds, but the transition maps are holomorphic maps. But in practice, this is not the definition that is used. Another definition is the following. So a complex manifold is a smooth even dimensional manifold, and together with the tensor, a smooth tensor of degree 1, 1. So this means that it gives an endomorphism of the tangent space at its point that we call J, and J satisfy J squared is equal to minus identity. So this first part, J squared is equal to minus identity. This basically just means that we have a GLNC structure, and this is called an almost complex structure, and then we have another integrability condition here, and we need this integrability condition to make sure that this definition and the usual definition are actually equivalent. So these are equivalent by a theorem. It's called the Nullender-Nirenberg theorem, and it's a non-trivial theorem. And yeah, so in practice, we will be using this second definition because we will be making use of this complex structure that this J is what we will call the complex structure. So since J squared is equal to minus identity, therefore the eigenvalues of J are either I or minus I. Therefore, if we look at the complexified tangent bundle, it could be split as the 2 parts. The first is the I eigenvectors, and the second is the minus I eigenvectors, and these are 2 subbundles. And in terms of local coordinates, like local complex coordinates Zi, these are spanned by dzi and dzi bar. So T10, the 10 part, this is called the holomorphic tangent bundle, and this is spanned by the dzis. And this is the anti-holomorphic tangent bundle. These are spanned by the dzi bars. So same way, when we look at the complexified differential forms, these are split as the sum of PQ forms. So the PQ forms are the same thing. These are P times holomorphic parts and Q times anti-holomorphic parts. So in local coordinates, these are the sum of some coefficients, some holomorphic some coefficients Fij, and we have dzi and dz bar j. So Fij is not necessarily holomorphic. So, and then we have what we call the Dolbeault operators. So these are, we look at the exterior derivative d, and we project into the p plus 1 q part. This is called del, the del operator. And the del bar operator is projecting into the q plus 1 part. So these operators satisfy that, well, the exterior derivative is the sum of these. So it's either projecting on the p plus 1 q part plus projection into the p q plus 1 part, and they satisfy that d squared plus del bar squared, d squared is 0, del bar squared is 0, and del bar plus del bar del is equal to 0. So what this means that these are can define a cohomology. So because we have del squared is equal to 0, del bar squared is equal to 0. We have a cohomology, and this is called the Dolbeault cohomology. So for this Dolbeault operator. So this is a recall of some basic notions in complex geometry. And now we look at Kähler manifolds. So Kähler manifold is a certain type of complex manifold with additional structure. So first of all, it's a Hermitian manifold. So this means that it's a complex manifold with a J-parallel Riemannian metric. So Riemannian metric, which is compatible with a complex structure. And in addition to that, we suppose that the two form defined by omega is J composed with the G composed with J on the first element. This will be a two differential form. We suppose that it is closed. So what this means that this omega, this is a non-degenerate two form which is closed, and this is basically the definition of a symplectic manifold. So here we will call G the Kähler metric, and the omega is the Kähler form. But in general, we will use both interchangeably. So sometimes I call omega the Kähler metric or something like that. So yeah, by this definition, Kähler manifolds are interesting manifolds which have three compatible structures. So they are complex manifolds, Riemannian manifolds, and symplectic at the same time. So we can study them from all these different perspectives. Another interesting fact about these Kähler manifolds is that when you look at the Riemannian holonomy groups, these are reduced to the unitary group. And this is actually even an equivalence. So being a Kähler manifold is equivalent to having Riemannian holonomy included in UN. So here I have to recall an important classification theorem from Riemannian geometry, which is the Berger classification. And this is a theorem which basically describes the possible holonomy groups of simply connected, non-symmetric, non-locally symmetric Riemannian manifolds, which says that basically we have, so the holonomy is always included in, sorry. So it's always included in your ON, but we could have holonomy in SON. These are the orientable Riemannian manifolds, and then we have UN. And here we get to, so Kähler manifolds are exactly the Riemannian manifolds which have Riemannian holonomy included in UN. And next,
Okay,
sorry,
Oussama, you mean half of n, yeah?
a half? Yeah. Sorry. So yeah, I mean 2n, yes. Or 2n here, yes. So wait, n to n, yeah, yes. Because we're considering even dimension. So yeah, and the next step in the Berger classification is holonomy included in SUN, and this will be of important interest in our case. We will get back to that later. But for now, Kähler manifolds are Riemannian manifolds with holonomy in the unitary group. Okay, so first of all, we will look at what are the examples of Kähler manifolds. So the simplest example is Cn with its Euclidean metric. And then, of course, by restriction, the complex sum manifolds of Cn are also Kähler. But as a fact of complex geometry, all complex submanifolds are submanifolds of Cn are actually non-compact. So there is no compact complex submanifold of Cn. So if we want to look at compact manifolds, the most important example it is the projective space. So CPN itself is a compact Kähler manifold. The well-known Kähler metric on it is known as the Fubini studied metric. And therefore, by the same logic, complex submanifolds of CPN themselves are also Kähler by the restriction of the Fubini study metric. And here, this gives us examples of compact Kähler manifolds. But a well-known theorem from algebraic geometry is Chow's theorem, and of course, the extension by like the far-reaching extension by the Serre's geometric, the Gaga theorem. So complex submanifolds of CPN are necessarily projective varieties. So supposing closedness. So what this means that they are defined by homogeneous polynomials. So they are not just defined by any holomorphic functions, but they are the vanishing of some polynomials in CPN. And these are always compact. So these are important examples. And so an opposite to this fact is that there is a well-known theorem known as Kodairo's embedding theorem, which tells us when a Kähler manifold is actually projective. So it means a projective variety. And this is Kodairo's embedding theorem, which says that a compact Kähler manifold is projective if and only if the cohomology class defined by the Kähler form is integral. So remember that the Kähler form is a closed two-differential form, so it defines a cohomology class. And so if this cohomology class is integral, then the Kähler manifold can be embedded into CPN, and therefore it is a projective variety by Chow's theorem. And if and only if it admits an ample line bundle. So this is a notion of positivity of line bundles. This is also an equivalent condition for being projective. So for this reason, Kähler geometry is very related to projective algebraic geometry. So lots of questions in Kähler geometry need the use of some algebraic geometry, and lots of questions in algebraic geometry are motivated by questions in Kähler geometry. So now some properties of Kähler manifolds. So one of the most important properties of Kähler manifolds is that they satisfy what's called the del-del-bar lemma. So this means if we have a PQ form which is exact, so it means d alpha is equal to 0, the alpha is d of certain gamma, so this is not closed. So if alpha is exact, then there is a beta such that alpha is I del-del-bar beta for some p minus 1, q minus 1 form beta. So this is satisfied locally in complex manifold, but we have this globally on Kähler manifolds. So in particular, if we have two Kähler forms, omega 1 and omega 2, which are in the same cohomology class, so that the difference is exact, it's an exact 1-1 form, then we have omega 1 is equal to omega 2 plus I del bar, a 0-0 form, which is just a smooth function view. So this is important for doing analysis because we can work just with functions here. Another fact of Kähler manifold is that we have the Hodge decomposition theorem. So for closed Kähler manifolds, which says that the kth cohomology with the coefficients in C can be split as these are the Dolbeault cohomology groups HPQ. So another thing about the Kähler manifolds is that we can define what's called the Ricci form. So this is the Ricci tensor composed with a complex structure J. So we call this rho. This is called the Ricci form. The fact about the Ricci form is, first of all, it is closed. It's a 1-1 form. And most importantly, it represents the first term class of the manifold. So it is a closed form which is included in the first term class of the manifold, which is a cohomology class. So this is very important. Another fact is that if we have two Kähler forms, omega 1 and omega 2, then the difference of the Ricci forms, omega rho 1 minus, so rho omega 1 minus rho omega 2, is given by, it has a potential, so it's minus I del bar, and it's the logarithm of the quotient of the volume forms. So this is omega 1 to the power n, it means the wedge. These are the volume forms of omega 1 and omega 2, and the difference of the Ricci form is I del bar logarithm of the quotient of the volume forms. So now we get to an old conjecture. It's called Calabi-Yau conjecture, which is a converse to this point here. So here we said that the Ricci form is closed 1-1 form and it represents the first germ class. So Calabi-Yau conjecture says basically the opposite. So if we fix a Kähler form omega, then all closed 1-1 form rho, which is in the first germ class, there exists a unique Kähler form omega phi, which is in the same cohomology class as omega. Sorry. Such that the Ricci form of omega phi is equal to rho. So this means that once we fix the Kähler class, in every Kähler class, there is a unique Kähler form which has Ricci form described by rho, which is any closed 1-1 form in the first germ class. So this was Calabi-Yau conjecture. This was solved by Yau in 77 and 78. So the particular case was the first term class of the manifold is equal to 0. So in particular, we can take rho here to be equal to 0 itself. So it's the 0 everywhere. So by this conjecture, the proof of Yau, there exists a unique Kähler form in every Kähler class, which has Ricci form is equal to 0. So this means that it's a Ricci-flat. So once we have vanishing first term class, there is a unique Ricci-flat Kähler form in every Kähler class. So what I mean by Kähler class, I mean any cohomology class which admits at least one Kähler form. So this is important because, first of all, well, it's always important to find the Ricci-flat metrics, because these are in particular Einstein manifolds, but they're also Ricci-flat. And actually, up till today, these are actually this is the most important way to produce Ricci-flat manifolds, Riemannian manifolds. And these, we will define Calabi-Yau manifolds. So it's Calabi-Yau because it comes from Calabi-Yau conjecture and Yau's solution. Calabi-Yau manifolds, these are any Kähler manifold which has first term class is equal to 0. So here we will use this definition. So in whether X is compact or non-compact, but this conjecture here proved by Yau, this is proved for X is a compact closed Kähler manifold. It is not a result in any general Kähler manifold, whether compact or non-compact. So here, this conjecture supposes that X is closed manifold. So now these manifolds, Calabi-Yau manifolds, meaning Kähler manifolds with the vanishing first term class, when we look at their Ricci-flat Kähler metrics, these have local holonomy in SUN. So what I mean by local holonomy, this means that a holonomy generated by just the the contractible loops. And another fact is that when we look at the canonical bundle of X, so the canonical bundle is the determinant bundle of the holomorphic tangent bundle. So if this is trivial, then so we know that the first Chern class of the manifold is equal to minus the first Chern class of the canonical bundle. So if in particular, if the canonical bundle is trivial, then the first Chern class of the manifold is equal to zero. And this is actually the most important way of producing Calabi-Yau manifolds. So these are Kähler manifolds with trivial canonical bundle. Sometimes this is used itself as the definition of Calabi-Yau manifolds, but this is a bit stronger than supposing that the first Chern class is equal to zero. So yeah, the definition Calabi-Yau manifolds differs from one reference to another. So when the canonical bundle is trivial in this case, so the full holonomy of the Ricci-flat Kähler matrix is in SUN, and these are important for string theory compactifications because so in the axioms of all the different, so here the accurate term is not string theories because there's not just one, but yeah, manifolds with the holonomy in SUN satisfies the supersymmetric conditions that arise from string theory. So this is one of the main reasons that pushed the people to study these manifolds. So other than the fact that they are the manifolds with holonomy SUN, so they are included in the Berger classification, but they also appeared at the same time that string theory started becoming more famous and more trendy in a sense. So before going to discuss the solution of Yau, so here I said, so if the canonical bundle is trivial, then the manifold is Calabi-Yau. And so this is usually the main way of producing Calabi-Yau manifolds. So for example, we can look at projective varieties which have trivial canonical bundle. And how do we get trivial canonical bundle? Usually we get that by the adjunction formula. So for example, any n+1, any hypersurface of degree n+1 in CPN, by the adjunction formula, which describes the canonical bundle, we get that the canonical bundle is trivial, and therefore it's a Calabi-Yau manifold. So this is the way of producing Calabi-Yau manifolds. Projective varieties with trivial canonical bundle. So how is Yau's solution of Calabi's conjecture given? So it is given by reducing this problem into a complex Monge-Ampere equation. So this is a PDE to be solved. So how do we get this PDE? So we will discuss it just in the case where Chern class is equal to zero. So if the Chern class is equal to zero, we start with any Kähler form omega, and we look at its Ricci form. So since we know that the Ricci form is included in the first Chern class, then it must have a potential because this is equal to zero. So it's ideal del bar V for some smooth function V. So V is not unique, but it's unique up to an additive constant. And therefore, if we want to find some omega phi, which has the Ricci form is equal to zero, then by what we said, the difference of the Ricci form is ideal del bar logarithm of the quotient of the volume forms minus V is equal to zero. And this means that what we have here is is a constant, and we can fix v by integration. We can fix that a constant by integration. So this is equivalent to saying that the difference of the volume forms is exponential of v, and since we want omega phi to be in the same cohomology class as omega, this means that it gives us omega plus I delta bar phi to the power n over omega n is equal to exponential v, and this is the PDE to be solved. So omega is fixed, v is the potential of its Ricci form, and we're trying to find phi, which is just a function which satisfies this equation. So omega plus I delta bar phi to the power n, etc. So this is the complex Mongeau pair equation that we want to be solved. So if we expand even further this equation will be given in the following way. So this is the Laplacian of phi is equal to exponential of v minus 1 plus some terms of higher order. So these are quadratic terms, but they involve not only phi, but also I delta bar phi. So this will show us that the equation is fully nonlinear. And Yau solution is done by the continuity method. So for the openness, we just need to study the linear part, which is the Laplacian. But for the closeness, Yau's contribution is establishing certain estimates that allow for the solution of this equation. So now we look. This is introduction to Calabi-Yau manifolds. So now we look at Calabi-Yau conifolds. So as we said, Kähler geometry is very much related to projective algebraic geometry. So in general, lots of varieties in projective varieties are actually singular. They're not necessarily smooth. So we want to know if there is a version of Yau's theorem, so Yau's proof of Calabi's conjecture, in the case of singular Calabi-Yau varieties. What we mean by that is that these are singular projective varieties with trivial canonical bundle. So as we said before, Yau's theorem is just in the case where the Kähler manifold is closed. So for the singular case, the answer is yes. This is a theorem from 2009 by Assidieu, Gedge, and Zeriahi, who proved that projective varieties with trivial canonical bundle and an additional condition on the singularities. So they suppose that the singularities are canonical. So these are, so not to get into details, these are just to say that the singularities are not too bad. So if we suppose this in addition, then these admit Ricci-flat Kähler metrics on the regular part, so away from the singularities. And near the singularities, they have locally bounded potentials. So this will be Kähler metrics on the regular part, and they are singular at the singular parts of the varieties. And we refer to these as singular Calabi-Yau metrics. So this is the most general way of generalizing Yau's theorem to singular varieties. And so this result, so it proves existence and also uniqueness when supposing the Kähler class. But what it does not do is that it doesn't describe what these Ricci-flat Kähler metric look like near the singularities. So it says nothing about their relation to the singularities. So a question to be asked, that was asked since the proof of that result, is that can we say something about what the metric looks like near the singularities if we know the analytic type of the singularity? So if we suppose that we know the germ near the singularity, so this is a complex information, can we say something about what the metric looks like? So a partial answer, not in the general case, is given only in 2017 by Hein and Soon, and it was later improved to take off some initial conditions that were imposed, proves that if a Calabi-Yau variety is analytically conical, so this means that it has isolated singularities modeled on a Calabi-Yau cones. So what this means, it means that near the singular points, this is the locally there's a local neighborhood, a neighborhood of the singularity, which is analytically isomorphic uh, to a neighborhood of the vertex in a Calabi-Yau cone. What we mean by Calabi-Yau cone, this means that it's an affine cone which has trivial canonical bundle. Therefore, it has Ricci-flat. They also have Ricci-flat Kähler metrics, and these Ricci-flat Kähler metrics, they are conical, so they are Riemannian cones. So they are of the form dr squared plus r squared times the metric on the link. So Calabi-Yau cones are in particular Riemannian cones, and with the Ricci-flat Kähler metrics. So if we suppose that a Calabi-Yau variety has singularities which are locally like a neighborhood of the vertex in a Calabi-Yau cone, in the analytic sense, in the complex sense, then the Calabi-Yau metrics, any Calabi-Yau metric on this is locally asymptotic. So it is asymptotic near the singularity to the metric of the cone, of the Calabi-Yau cone. Basically, the most simple way of saying is that if they are analytically conical, then they are metrically conical as well. So this was proved by Heinz-Sung and improved later. So the proof is very it's again a continuity method, but it's very complicated because they need the use of some notions of Gromov-Hausdorff limits of Kähler manifolds. This is a theory developed by Donaldson and Sung. It's the same Sung here, but yeah, the proof is very complicated, but yeah, this is the result proof. So what are some examples to apply this result to? So the most important example to keep in mind is the following. So we look at Calabi-Yau varieties which have isolated nodal singularities. So what we mean by nodal singularities, these are singularities that are locally isomorphic to the cone given by z in Cn plus 1, such that the sum of zi squared is equal to 0. So these are the simplest possible singularities to look at. So an example of such varieties. So if we look at a projective hypersurface of degree n plus 1, so first of all, this we said that has trivial canonical bundle, in particular it's Calabi-Yau variety, and we suppose that near the singular points, we have non-degenerate Hessian. So if the Hessian is non-degenerate at the singular points, then it's easy to see that the singularity is therefore isomorphic to this node singularity here. So this cone, this is a cone in particular because, well, if we look at lambda zi's here, it will remain in C as well. And it also has a Calabi-Yau cone metric, an explicit one. This is called the Stenzel metric. And it's given by I del bar, and here we have the norm of z squared to the power n minus 1 over n. So this could be seen, could be proved to be a Ricci-flat Kähler and a cone metric in the Riemannian cone sense. So by Heinz-Sung's result that we described before, what it says is that if X is a Calabi-Yau variety with singularities that are locally like this cone, then any of their Calabi-Yau metrics, what we say Calabi-Yau metric means Ricci-flat Kähler metric, is asymptotic near the singularities to the Stenzel metric. And this should be kept in mind to be like probably the most important example. These are like the simplest uh, singularities to have. So now we move to something else. So an important natural process in algebraic geometry is to desingularize singular varieties. So we will look at two ways of desingularizing singular varieties. These are resolutions and smoothing. So these are algebraic processes of turning a singular variety to a smooth one. So a resolution, so before looking at this definition, a resolution basically means that if we have a singularity like this, we want to replace the singularity by a subvariety. So if this is singular point X, we want to replace it by E. We keep everything else the same. Elsewhere, it remains the same, and such that the resulting is a smooth variety. So if this is X, we call this X hat. And what this means is that there is a birational map from X hat to X, such that, well, this is non-singular, and such that away from so away from this subvariety and away from this point, we have a biholomorphism. So this is a resolution. Basically, we keep everything the same. We just replace the singular point by a subvariety. So there are algebraic ways of doing this, usually by something called the algebraic blowup. And the second way is by smoothing. And this is a different way. This means that we look at our singular variety X. Well, it is defined by certain polynomials Piz. And we perturb the polynomials by certain t. So something like, not necessarily like this, but something like Piz is equal to t, such that the resulting fibers for t different from 0 are non-singular, are smooth. So a way of describing this means that a smoothing is a deformation from this calligraphic X, which is a variety of one additional dimension, and this is the unit disk like here, such that the image of 0 is the singular variety X, the original singular variety, and the fibers for t different from 0 are smooth. So these two ways of desingularizing are different, but because in this case we're keeping the whole variety the same, we're changing just the singular point by subvariety. Meanwhile, here we're moving the whole complex structure we are doing a deformation of the whole complex structure such that the fibers are now smooth. So if the resolution is what we call Kerpont, this means that the image, the inverse image of the canonical bundle is the canonical bundle of the new variety, then the new variety itself is Calabi-Yau. So because this will be trivial as well. So it's smooth Calabi-Yau. Same thing, if the smoothing has what we call trivial relative canonical bundle, so this means in particular that there is the canonical bundle of each fiber is trivial, then the fibers are also smooth Calabi-Yau. And therefore, by Yau's theorem, we know that they have smooth Ricci-flat Kähler metrics in every Kähler class. So there is a process where we start with a smooth Calabi-Yau, then we will contract certain subvarieties, as like in the case of resolution. So we have varieties like this. And we contract this this E. This will to get a Calabi-Yau conifold, and then we pass to the smoothing on the other side. So this is not always possible. We don't always have a smoothing, but when we have such a smoothing, this process where we start from this, contract subvarieties to get a conical Calabi-Yau manifold, and then we do a smoothing, this is called conifold transition. So this is important because we start with a Calabi-Yau here, we get Calabi-Yau here, and they are both smooth, but in the process, we're changing the topology. So we're producing new Calabi-Yaus from old one and changing topology. So we're producing non-homeomorphic Calabi-Yaus. And a well-known conjecture on Calabi-Yau manifolds is that, which is called Reid's fantasy, claims that any two Calabi-Yau threefolds, so this is just in the three-dimensional case, but it can be extended in higher dimension. Well, threefolds are important because they appear in string theory. That's why, because you have 6 additional dimensions. So Reid's fantasy says that any two Calabi-Yau threefolds can be connected by a finite sequence of Calabi-Yau conifold transitions. So we take any two Calabi-Yau threefolds, we contract some subvarieties to get conical Calabi-Yau, we smooth, and then we contract some other subvarieties, we smooth, and we do a finite sequence of these two, and we're changing the topology at every step. And this conjecture, it says basically that any two Calabi-Yau manifolds can be connected by such transitions. So this is how we imagine these conifold transitions. So we have this X hat like here, we have these subvarieties. We are contracting these subvarieties such that locally we have something that looks locally like a certain model cone. And then we do a smoothing and we have these fibers XT. And so this will be the motivating question for our result. Is there both of these processes? So this is the resolution on this side and the smoothing on the other side. These are algebraic processes, so we're just doing something algebraic. We are either doing a resolution, algebraic resolution, or algebraic smoothing. This is a deformation, and this is a blow up, or whatever type of resolution is done. And well, the question is that, is there a way of realizing these algebraic processes, the desingularization, so resolution and smoothing, in a metric way? So can we put metrics on these processes? So more precisely, can we see the conical Calabi-Yau metric on X? So we said that if X is conical in the analytic sense, then it is conical in the metric sense. So it has conical metrics. And so can we see this conical Calabi-Yau metric on X as a limit or a degeneration of some families of smooth Calabi-Yau metrics on the resolution X hat? So can we find some family of Calabi-Yau metric, smooth Calabi-Yau metric on X hat, such that, well, when epsilon goes to 0, we get the conical metric on X. And we can ask the same question in the case of the smoothing. So can we have Calabi-Yau metrics on the fibers? which when we let t goes to 0, we find this conical metric on X. So this is the main question of interest. And also, we want to, if we can find such metrics, such Calabi-Yau metrics, we ask, can we describe the regularity of such degeneration? So can we say more about such degeneration? So one of the interests of looking at such of transforming these the singularization process, which are algebraic processes, to something metric, is that this would allow of doing analysis. So we could study, for example, the degeneration of the Laplacian. We can look at some invariants, for example, something like what happens to the holomorphic analytic torsion, what happens throughout this degeneration, and so on. So what was just algebraic can be turned into something metric, which therefore can be used to study analytic problems. So in a way, this would allow us to, for example, if for example, we suppose that Reid's fantasy conjecture is false, then there should be an obstruction to be found, and that such obstruction should be some sort of invariant. And studying such invariants would need us to do analysis throughout these processes. So this is one of the motivating things for that, for this question. So I will stop here for the first part before we go to the second part.